Okay guys, we're going to go over lab number 6. This is meant to be a review of thermodynamics. I'm going to start us off at problem 12, which asks, was the combustion exo or endothermic? The answer to this is exothermic, which will give this value a negative sign. This was because this reaction released heat. Write the balanced reaction for the combustion of candle wax, C25H52 plus 38 oxygens. It's going to go to 25 carbon dioxides and a certain number of H2Os. That would be, I believe that would be 26. Yes, 26 H2Os. There's the combustion reaction. Up here, if you have 0.28 moles of C25H52 reacting, you're going to go up to your mole ratio, which is going to say that 1 mole of C25H52 is needed to produce a certain value of kilojoules per mole, which you solved for in the last problem. So you're going to go there, put the number here, and multiply, and you're going to get your answer in kilojoules. Notice the units are not kilojoules per mole because the moles do cancel. For this reaction, delta S is going to be greater than 0. It gets messy. You go from 39 particles on the reactant side to 25, 51 particles on the product side. So delta S is greater than 0, delta S is positive. Going to 16. Based on the enthalpy and entropy values, discuss the spontaneity. All right, delta G is going to be equal to a delta H, who's negative, minus a T times a positive. We can make that a minus plus a T times a minus, and when temperature goes to 0, delta G is going to be less than 0, and if temperature went to affinity, delta G would still be less than 0. So this reaction is going to be always spontaneous. Common question on the test. All right, we're going to grab our value from above, and we're going to do some bond energy problems with that. We know because we saw the word bond here and we saw the word bond here. Immediately, we're going to write our formula, which is the sum of the bonds broken minus the sum of the bonds formed. Our reaction, we could say C above. I believe that was number 12, 13, one of those. The loop structures for paraffin is really tough, but what you really want to focus on is there are 52 CH bonds in there. And there are going to be 24 C bonds in there. And you can come and discuss this with me in class if you're not understanding that. We do have 38 O double bond O's going to our 25 CO2s plus our 26 waters. All right, we're going to plug this information into our bonds broken minus bonds formed equation. I'm going to try and do this as clear as possible. For bonds broken, I do have 52 carbon-hydrogen bonds. So 52 times 413 for the carbon-hydrogen bond. That's going to be plus 24 times the 347 for the carbon-carbon bond in this case. We are also then going to add that to 38 times 495 for the oxygen bond. We're going to subtract that from the bonds formed. Bonds formed, we have the carbon dioxide, which will be 2 times 799 times 25 for the 25 carbon dioxide, you can put that in parentheses, plus 26 times 2 times the oxygen-hydrogen bond, which is 467. So we're going to add these up here and get a number and subtract it from these, and that's going to give you your overall delta H in kilojoules per mole. I'll let you guys do the math on that one. Okay, on this one, I just want you to compare your actual value to your theoretical value. Sometimes they'll have you calculate what's called a percent error, and you can look on the internet to find out what that calculation is. I encourage you guys to do that. What I really want you to do here is just discuss it. Talk about if they were similar, if they were different. Okay, in this question, we're talking about heats of formation. So I asked you to take your value from above that you just calculated using your bond energy and calculate the heat of formation for this particle. So delta H, when we're talking about heats of formation, is the sum of the products minus the sum of the reactants. In this case, you solve for your value from above, so some kilojoules, you solve for. Your products, in this case, are going to be your CO2s. You had 25 CO2s, and the value they're giving you for CO2 is negative 393.5. And you had the waters, I believe you had 26 waters, they're giving you negative 242. And you're going to subtract that from your reactants. In this case, it's X plus, I believe we had 38 O2s, but we all know that this goes to 0 when we're talking about delta H. So you're going to subtract those and you're going to get your answer. It's going to be in kilojoules per mole. What I'm really concerned about is the process more than anything. All right, specific heat is essentially how hard it is to heat it up. We got water and we got ethanol. Okay, both of these are polar. This one is polar with 2 H bonds. This one is polar with a 1 H bond. The 2 H bonds makes this one harder to heat up. It's a stickier particle. Oops, sorry about that. Okay, moving on, they're asking for an energy diagram. This is going to be energy. This is going to be time. I'm moving kind of faster because I don't have 10 minutes to do this. This is going to be your change in energy. This is less than 0 because you end up at a lower place than you started. This is your activation energy hill. Note it's a very high EA. In this question, they're asking us to agree or disagree with this statement. I'm going to disagree with this statement. Increase rate by pushing uphill. Only a catalyst decreases the energy of activation. Remember, guys, a catalyst does that. That's what a catalyst does. Okay, this is not a catalyst. This helped push it up the hill. That was the function. So please email me if you have any more questions, and take care, everybody.